Verjovsky from Cuernavaca, and he will lecture about the moment and/or manifolds, intersection of quadrics and higher dimensional compact manifolds.
Thank you. As usual, I stand organizing thank you. I'm very glad to be here. I congratulate Pepe on his 60th. He's been my collaborator and friend for many years. I think everything has been said about him, but I would like to emphasize the importance he has in the development of mathematics. So thank you for that. So that's the title of my talk. This is a collaboration with Danita. He's a student of the Washington man in Cuernavaca. And in related to singularities, I will tell you in which way. So I want to describe new examples of compact manifolds, finding here in arbitrarily high dimensions. By the way, these manifolds have already been mentioned by the talk of Santiago Lopez and Milano. We didn't get together to see what we do. But still, what I speak is different, has a different thing. So these manifolds are modifications, certain so-called Roman angle manifolds, which were obtained several years ago by Santiago and later generalized by Laurent in this conference. And in fact, these examples were obtained as a consequence of a seminar in the in which Pepe was present. When Santiago gave a gift to Pepe, he referred to 1986 as about the time a little later started. And these were generalized by Laurent in this beautiful paper that I will give later. And the results here will appear in this captions, as you can see, just appeared last month. They are online already. So let's start at the beginning. So you take an integer greater than 3, and you want to study what Santiago probably defined, system of quadrics. So here in this, the lambdas are complex numbers, and this is in Cn, and you have as many as first you start with only one equation, and you take this equation, and so this will be something like a mixed type like Professor Rocken, so it's somehow like that. And you intersect with the sphere, and but I see if there was one equation, no, actually there are n equations. I don't see whether this lambda is Blackboard, is a vector. So lambda is a vector, so you have n equations. Think of this as a vector weighted by that. So it's actually n real equations. And well, this of course the topology will be completely determined by the lambda i's. And we want this lambda i's to satisfy certain conditions, which I call what we call the admissibility conditions. I think Santiago likes a different name, but we study first, start with the case n equals to 1. That's to say only one equation like that. So you have n vectors in the plane, and you have this equation, and it looks like very simple, it's an intersection of quadrics. Okay, but actually there's a theorem that says that any stable parallelizable manifold, any manifold that has a stable normal model, is actually an intersection of quadrics. But maybe not homogeneous. But that means that intersection of quadrics is practically all manifolds, all compact intersection manifolds. Okay, so well, these manifolds have extremely rich topology. We proved, Santiago proved in one of his early papers, Santiago proved that these manifolds are, in general, connected sums of closed spheres. And which is very surprising, these manifolds can behave as a real analytic manifolds in complex projected space of some dimension. And as you can see from the so I try not to be very technical. This is the last conference in the world study, yes, it was a party. So I try to say it more with my hands. You see those equations? Well, actually, if you take the vector z1, zn, and you multiply by a collection of complex numbers, e to the I theta 1, e to the I theta 2, the equation remains the same, because the norms are 1. And therefore, in a natural way, this manifold achieve an action of a torus, a real torus, t to the n, in an obvious way, by multiplying the coordinates by unit complex numbers. And the surprising thing is that these manifolds, even though they are not holomorphic, they are not complex manifolds, there's a subaction of this torus action, which is free and proper, and whose quotient is actually whose action is locally free, and whose quotient is a toric variety with simple singularities, with quotient singularities. And the surprising thing is that any toric manifold, in the algebraic sense, if you will, the closure of a C star to the M action, C star to the M action, any toric manifold with simple singularities is obtained this way. And I like to say the cliché that therefore algebraic geometry is just, some parts of algebraic geometry are just a chapter of the dynamical systems. But I was pointed out by the algebraic geometry that a toric variety is by definition obtained by dynamical systems, because the closure of an action is star to the end. So I was defeated in my arguments, but I still think mathematics is an essential thing. It's a very essential thing. So this is your machine to produce infinitely many new examples of C-infinity manifolds with actions, torus actions, and sometimes they have quotients that are actually very beautiful complex manifolds. You know, they're actually toric manifolds, infinitely many new examples. Well, these manifolds are known, especially in the Russian school, by Gustave and Panov, are known moment angle manifolds. And these manifolds depend on here lambda, depend only on the matrix of vectors, lambda 1, lambda 2, and the dimensions. And they are always principal certain bonus over complex surfaces, which are never catered, by the way, except in a few cases. These manifolds have also been extensively studied by the Russian school of Gustave and Panov, among other people. And they are interesting also because they have natural open book structures. They need different geometric structures, such as almost complex structures. And since these manifolds appear as neat locally free actions of R to the K, they automatically, in an obvious way, Poisson manifolds. In the obvious way, we have an action of even dimensional, a locally free action of even dimensional Euclidean space. So now, under which conditions this is actually a manifold? Well, the equations are homogeneous. That means that this is a cone. And to understand a cone, as was explained by Santiago several times, it's enough to understand its intersection with this scale. Like for Briscoe singularities, same idea. Now they want to be Briscoe manifolds, they are not, they are just real analytic manifolds. But still you need some transversality conditions. And the conditions are these. Must satisfy these conditions. The first condition, to be non-empty, is that 0, so you have this collection of vectors in Cm. For one equation, you have n vectors, you have this collection of vectors, and then you take the convex envelope, and one condition for this manifold not to be empty is that 0 is in the interior. So the convex set appears for the first time in an obvious way. It's a convex closure of the values which determine the equation. Convex set. So we have that. And the second that sounds a little complicated, simply the only thing it means, this condition is secondary, is that 0 is not in any of the diagonals. So think in the case of one dimension, it's a polygon, and then you take all the diagonals, and 0 is not in any of the diagonals. This is one of the chambers in which the diagonals separate the convex set. And you have higher dimensional convex set, you have faces, divided into chambers, and 0 should be one of these chambers. So this is called the weak hyperbolic condition. And then you have this theorem. And this is the result. This is just a technical lemma. I don't want to go to, I told you I don't want to go to technical lemmas. This is the technical lemma you need to prove that the Jacobian doesn't vanish, and therefore that this defines actually, this hypersurface is given by each of the quadrics. It's not singular except outside of the origin, and outside of the origin they meet transversely, and therefore they define a manifold. Since it is a cone, automatically is transverse to the sphere, and therefore we have a manifold. Under these conditions, technical conditions, you have a manifold. I think that was explained by Santiago, but I just repeat it here. Here's written by the told you. You know, it is the system is regular outside of the origin, and it's just written by the told you words. Technical condition to make sure that this manifold is not empty and is smooth. It's a smooth cone, singular point at the origin. And here's what I told you also, is that there's a canonical action of the torus simply by what I said before, multiplied by complex numbers, unit complex numbers, U1, U8. You know? And you see, this is a torus of the Tn, and there exists a subtorus of this smaller dimension, so that the action is locally free. So this is an effective action of the torus, but manually free. But if you take, there is a subtorus in which the action is locally free. And therefore the quotient is an orbifold. In the case if it is free, the quotient is a manifold. Okay? And if you choose properly this torus, I told you already that the quotient is actually a complex manifold. Okay? So even though these manifolds, moment angle manifolds, are not complex manifolds, they are foliated in such a way, always have a foliation which is transversely carried. So, not so bad. We have a complex manifold, but they're foliated by transversely carried foliation. But I want a modification of, so I tried very hard to prove that these manifolds, which are odd dimensional, were contact manifolds. And I couldn't do it. I did get some result, I couldn't do it. So in one moment I tried to thought of modifying the equations, and this is a new equation in which I add n complex parameters. So it's exact. If you erase that one, it's the previous one. Okay? And now these manifolds are called moment angle manifolds of mixed type because now there's an action of z2 to the n, the group of order c2 to the n, the group of two elements. You simply change the coordinate, you change the sign of the omegas, and here multiply by the unit numbers. So in the mixed type, they have z2 is S0, no? It's a fancy way of calling this here. So they have an action, and the quotient again is an interesting object. Okay? We call this one moment angle manifolds of mixed type. And now there's a proposition which actually was suggested by Santiago, which is an expert in those questions, like the gift for Pepe was a solution of some of these problems. That tells on the which conditions these equations, these new equations, determine a manifold. when the quadric hypersurfaces are non-singular outside of the origin, and when they need a 2 by 2 Lie transform in order to have a manifold. And the condition is this, that every subsystem, you are raised some equation, you have a subsystem with less variables, less equations, and for each subsystem, the equation is good, is regular, the total is regular, it's a proposition. And you intersect this sphere. I mean, you see here we added the coordinates here to make the sphere, no? And we have this new manifolds here. Well, this is what I told you. This is good manifold if any subsystem is good. Well, as I told you, this is the technical lemma that Santiago Lopez de Verano offered to us, to Yanni and myself. And his definition. These manifolds are quasi-momental manifolds of type lambda n, and they correspond to this configuration. So every time you give a family of vectors, you have a convex set, which satisfies some conditions, and you have a complex manifold of that. And this is stable on the small perturbations of this condition. You move a little bit in convex sets, you still have the same manifold, but you might change the complex structure, etc. So my objective with this document was to get compact structure of these manifolds. Well, here the observation data is homogeneous, therefore. Okay, now here come. Okay, so in our space, which is Cm plus n, we take, so we have n w variables and n c variables, and you take this one form. This is a real one form because this part here is imaginary. This is imaginary, you multiply by s. So it's a real one form, and it's actually just the primitive of canonical Kähler form of Cn plus n. And if you take this form only, forget about the variable w. Take this form, I times this in Cn. And this is a beautiful form because, for instance, if you take a Bismarck manifold, which is a sum of powers of C1 to the A1, plus C2 to the A2, plus C3, etc. I don't know about mixed type, as a canonical C1 to the A1, C2 to the A2, etc. If you restrict this one form to that Bismarck manifold, you have a contact structure. And therefore, that is, in general, these links are contact, but in an explicit way. You know, this is the form that realizes as a contact manifold. And so I say, why don't I try with this new manifold, try to use the same form to see what happens. And I failed, but I tell you, I failed, but theorem says it's constant. Actually, I think API equals to 1. But it's more general, you can, okay? The form depends on parameters, on complex parameters. But forget about it, let's make it more general in the theorem. Think of them as 1, okay? I should have called the form alpha, so we make it 1 to examine, okay? You see here, I suppose that. Well, the first lemma, maybe this form, when you restrict to the tangent space of our manifold, becomes a trivial form. And then it doesn't define a plane distribution. So the first thing I have to be sure is to be sure that it actually defines a non-zero linear function in each tangent space. But that's the data. So the one form restricted to the tangent space to our manifolds. You see, when you put a 1, when I put a 1 here, it is, if I suppress the 1 is the cone in the deleted Cn plus 1. The deleted cone. And when I put a 1, for technical reasons, intersected with 0. So this is the compact manifold. And the first lemma is that this is a non-trivial form. So how do you do that? Just counting parameters. Okay, so you take, this is the lemma. You see? Just counting parameters on the one form that don't vanish, and you prove it. I will give you the proof. You take the lemma, calculation, counting of parameters. Well, this has a submanifold of coordination 2L is the submanifold where all the omegas are 0. So you intersect this cone with a hyperplane W1 equals 0, W2 equals 0, etc. Not just as it's not a manifold, but it's an analytic set of high coordination. That means it doesn't separate in particular. It doesn't separate in space. And now, this is what I say. I failed to prove, how do you prove that a form is a contact form? You take the kernel of the form, is exactly what the previous Professor Emiliano said, plane distribution, and you have to prove that the differential d alpha is symplectic in this. But it's the same thing as saying the kernel of d alpha intersecting the kernel of alpha is only 0. Because that means that it's non-degenerate. And unfortunately this failed, but has a constant drag. So this is very interesting. Has a small constant drag, so it's beginning to look like a Poisson manifold. And well, then you prove that actually the intersection of the kernel of an alpha, a alpha and alpha is integrable and is tangent to an action of the torus. So this is actually the Poisson structure. So these are canonical Poisson manifolds, which is already very interesting. Well, this is what I told you. Here you have the action of the symplectic action of the torus. Now this is a beautiful theorem. This is probably what I want to tell you. So, everybody started, so I constructed infinitely many new manifolds. There's a canonical one form, which is non-zero, which tangent space. It's not symplectic. But if I add the omega 1, omega 2, the new variables, this will be symplectic outside of this analytic set that I told you. And now this beautiful theorem of addition is set form. So you take the set of points where alpha is a contact form, namely satisfy the condition of the previous lectures, alpha exterior T alpha to the n. N is the dimension. It's non-zero at every point. It's an open set of the manifold, maybe empty, but suppose it's not empty, and suppose any point can be connected by a Legendre curve, like in the previous lecture, so it's going by distribution to a good point. So you go, like an airplane, you go tangent to the distribution, and finally you come to a beautiful place where the structure is contact. And then a beautiful analytic theorem, of which I didn't understand very well the proof, it's a well-established article, a very solid article, says that the theory of partial differential equations via the maximum principle tells you can perturb arbitrarily small in this infinite topology, the one form. So you tilt a little bit the plane distribution and you make it a contact form. Fantastic theorem, because via analysis you prove a real good theorem which is having contact structure. So when I saw this theorem, first I couldn't do it because my form was 0 in a real codimension 1 submanifold. And so, terrible. But now, the set of back points has high codimension, and therefore doesn't disconnect my. And then I use that to make the contact, and therefore this gives an infinitely family of new contact manifolds with extremely rich topology. And we have it's part of the homework for Santiago, but it has been too busy to determine the topology of these manifolds. These manifolds are at least as complicated as connected sums of products used. But most probably, the conjecture is that given any finitely generated building group, this is a direct sum of the homology of the manifold. In other words, this will give you contact manifolds arbitrary topological complexity. And I saw that they gave you these technical things such as heat the refrigerator a little bit, use the heat flow, and propagate it to get a contact structure. And simply I finished by, well, this is foliation by Thornton. So, hang on. This means that outside of a coordination 2, alpha exterior d alpha to the n is non-zero, and it's always greater or equal than 0. So that's what Thornton calls confoliation. There's no negative and positive. There is strictly positive. It is 0 means foliation, and with different from 0 means contact. And that's the way it does it. And, well, I finished by, well, all these blah, 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 technicalities, Altshuler. What I can say about that is that, in some sense, it's explicit because the heat flow gives you a formula for the small perturbation. So even though I don't give the form explicitly, in some sense, you put it in a computer, and you get the coefficients of the form. So, in some sense, it's arbitrarily close to the form I give you, and explicit quotation marks, maybe a computer you get it, a concrete form. And finally, these manifolds are topologies totally determined by something like the momentum map. You see, I told you that you have two convex sets. The first convex set is a configuration of lambdas. And the second convex set is because the action of the torus has, like any bubble map, has a quotient that is a convex set. So you have two convex sets. One is actually the gauge transform of the other, it's a combinatoric. And the whole topology is completely determined by these convex sets, by toric varieties, no? They play the role of not the fan, but something like that. And therefore, we have some hope that we can actually get into the richness of this theory, but so far we have been able, as complicated as we're just beginning. And so with that, I finished very quickly, and you're more or less quickly, and now you can rest. That's all.
Is there any questions?
I want to thank everybody for my questions first.
I would like to know why do you call the moment angle?
Because of physics. So we see the torus moment angles of positions and angles like
It doesn't appear in your lecture.
No. It's a name, I told you, it's a name used by Altshuler.
Microphone.
By the Russians.
Microphone.
It's a name given by the Russian school, which is very strong on that. Gustav especially, and his school. And they call it moment angles because it comes from physics.
Any other questions? So let's
explain a little bit because this torus, you have this torus, action of the torus, the quotient is a common polytope moment, and the angle, and thus is given by the toric. So he has a bunch of tori whose quotient is a convex set. So it's a very appropriate name, but also physics.
Thank you very much.
On the name of all the participants, including the organizers who will thank themselves, there is such a good word that they need to thank themselves. I would like to thank But I think it's better. First, I would like to thank Yahweh's Lucy, in my class. And then, I think he had a team, and I think it's fair that if he thanks his own team.
Thank you, Alberto. Maybe I would like to thank first all those hidden who were doing hard work. We haven't seen them for days, but they are there in what I used to call the kitchen. From 9 in the morning to 9 in the evening working. These are Liz, some of you know her, Edgar, El Contador, Olga, Olga also, I mean, she came as a volunteer to help us. Fernando, he's here. Thank you, Fernando. He came as volunteer, that he tried to help us, and he did a good job. So they were all working all day long, starting from Cuernavaca and continuing here, probably on January, helping for writing down the reports. So I really would like to thank them all. They did a good job for us and they wrote this for us. You have also seen Vanessa and Alejandro running all day long, taking papers, asking for signatures, selling t-shirts, and doing all what was possible. It's also, they started a long time ago also. And thank you, Vanessa. Thank you, Alex. Other people helped us, starting from Cuernavaca. Lucia, she was supposed to be helping just with the school, but then we could not finish without her, so she continued working with us for the meeting. Thank you, Lucia. From Cuernavaca again, people that could not really Cuernavaca, Mexico City, that could not be with us. Laura Ortiz, she worked hard for the school, she worked hard for helping us for the starting of this conference. She's not here with us. Thank you, Laura. His name doesn't appear in any list of either speakers, not organizers, not scientific committee, but he did a good job starting from the beginning. Awin, thank you. The colleagues from Mérida, Juan Pablo Navarrete, Valdemar Barrera, Ramon Petiche, they allowed us to have this wonderful space. They allowed us to, I did all the contact with university for getting things working on. I think everything worked quite well, very well. Thank you. Thank you, Juan Pablo. Thank you, Jose Luis, thank you. This work started more than 2 years ago. We started from zero, asking for people to get into it. And thank you. Please.
So, well, it was a hard work, but we all enjoyed doing it because it was a real honor for us to do it. Because celebrating 60th anniversary of Pepe, he has supported all of us a lot, the mathematics in Mexico in general, Singularities in particular, and I think also it was very important to gather this community of Singularities around the world, here in Merida, to hear about this wonderful subject. And we are very grateful also to all of you for coming here and making such a wonderful conference. Thank you very much.
Omega Calvo, who worked also with us for this, he helped to coordinate contact with Brazilian group. Thank you, Omega. Thank you for Edgar. Muchas gracias, Edgar. He's one of the bigger ones. I would like also to thank the scientific committee. They started also working with us on this more than 2 years ago. We had permanent and constant contact via email. Thank you all for your work, for your help, and for your support. This is probably preparing the party. So the party for today is going to be in the restaurant called Eladios. This is the same company as the one of last Friday, but this one is downtown, so the atmosphere is different. It's more dancing place with food, the same concept as last time. The address is on the street 59 at the corner with 44. That's short walk of 15 minutes. The appointment is there at 2 o'clock. There will be a van for those who prefer not to walk. Please take into account to leave the place for those who prefer not to walk. There are just few places available at the van. The van will leave at 10 to 2 from the Hotel Casablanca. And the address is
5944.
is street 59, the corner with 44. Please, por favor. Muchas gracias.
Nos vemos en la fiesta.